In this work, we aim to decompose videos into layers that the user can then use to easily perform edits like object removal or object retiming. In detail, the problem setup is we're given an input video and object masks, and our goal is to predict layers that each contain an object and its correlated effects, such as shadows or reflections. With these layers, we can then perform edits, such as removing the person and duplicating the dog. Existing methods are self-supervised, which is a strength due to the impracticality of obtaining labeled layers. However, a weakness is that they're slow because they require per-video optimization. Our solution is to take a data-driven approach by pre-training a single network on a large dataset of videos, which can then be quickly fine-tuned on a new video. One way we can think about this problem is as a cooperation game between different players, which in our case are network instances that each output a layer for a single object. We're inspired by the concept of a Schelling point or focal point from game theory, which is the strategy that players will adopt to cooperate when they're unable to communicate with each other. An illustrative example of this that Schelling proposed is the hypothetical problem of meeting up with a friend in New York on a Tuesday. A survey from that time found that a significant number of people say they would go to the information desk at Grand Central, so this solution would be the focal point of our problem. In the context of the OmniMat task, each player is a network instance that can see the input frames and the input masks for a single object and has to predict the corresponding layer for that object. These layers, when composited over the background, need to reconstruct the original frame. Thus, each object's reflection should go in its layer, making this decomposition the Schelling point of the game. However, in this setup, nothing prevents the players from outputting a bad decomposition, such as grouping all of the reflections with the closest object, for example. The challenge with this problem is that a bad decomposition reconstructs the frame as well as a good decomposition, so the losses for both solutions are the same. So if we can't rely solely on the reconstruction error for a good decomposition, we have to design the setup to encourage that correct solution. And we do that by changing the task from reconstructing the input to predicting future frames. We hide some of the input frames in the sequence and train the network to reconstruct those hidden frames. And this pushes the optimization towards the correct decomposition. In other words, player 1 sees all of the masks for object 1, but none of the masks for the other objects, so it has an advantage at reconstructing the effects for object 1. So every player is encouraged to reconstruct the effects for the object it observes. To train our network, we generate data using the Kubrick codebase to easily obtain a large dataset of videos with interesting shadows and reflections. Since our method is self-supervised, it can also be applied to real data. This enables us to perform fine-tuning on real videos during test time. We first pre-train the model in a self-supervised manner on synthetic Kubrick data. This network can be used for inference, producing a coarse layer decomposition in a zero-shot setting. In the second stage, we fine-tune the model on a single target video for 200 steps, and this process refines the reconstruction quality of the layers. We train a model on synthetic videos which contain 2 objects in a single scene. We then demonstrate its generalization ability by testing it on unseen 4-object videos. So here we show the input video at the top and the 4-object masks below. The result from Liu et al. Places many reflections in the wrong layer. Our zero-shot result assigns the reflections to the correct layer, but the reconstruction is coarse. After fine-tuning on this video, our model produces higher quality layers which closely match the ground truth. Not only is our result more accurate than Liu et al., it's also 10 times faster, with the fine-tuning process taking minutes. Here we show results from fine-tuning a pre-trained network on a real video of 2 people walking and casting reflections in the glass. We compare our fine-tuned result in the bottom row with the result from Liu et al. In the top row. Not only is our method much faster, our fine-tuned result actually has fewer artifacts and is more robust to random initializations. Thank you for watching. For more information, please visit our project page.